Industrial manipulator calibration. Welcome ladies and gentlemen to this short video about kinematic and compliance calibration of industrial manipulators. This video outlines 3 essential steps of the calibration procedure, and exemplifies its application on an ABB IRB 6700 industrial robot using a Leica T901 laser tracker. These 3 steps are the measurement and identification of the transformation of the laser tracker data into the robot's base coordinate system, tool transformation of the measurement point or points, as well as parameter identification. These steps are based on the state-of-the-art as utilized by robot manufacturers. Transformation of the laser tracker data into the robot's base coordinate system. To successfully calibrate the manipulator, the measurement data needs to be expressed in the robot's base coordinate system. The measured position data shall be expressed in the robot's base coordinate system. The base coordinate system should be measured and identified using the circle point method. The circle point method utilizes the following ideas. The position of the base coordinate system is given by the x and y coordinates of the circle inscribed by joint 1 and the z coordinate of the circle inscribed by joint 2. The orientation is the cross product of the normal vectors of the circles inscribed by joints 1 and 2. Let's take a detailed look at this idea. Circle point method, rotation joint 1. Here one can see on the left-hand side a simulation and on the right hand the equivalent on the ABB IRB 6700. By solely jogging joint 1 and maintaining all other joints, the SMR mounted on the mechanical interface of the manipulator as a target inscribes a circle in an XY plane of the robot. The circle is highlighted in red on the left-hand side. Circle point method, rotation joint 2. Then by solely jogging joint 2 and maintaining all other joints, the SMR inscribes a circle in the XZ plane of the robot. The circle is highlighted in black on the left-hand side. Circle point method, conceptual. This is a representation of the measured data in the laser tracker, that is using the laser tracker's coordinate system. As aforementioned, the position of the base coordinate system is given by the x and y coordinates of the circle inscribed by joint 1 and the z coordinate of the circle inscribed by joint 2. The orientation is the cross product of the normal vectors of the circles inscribed by joints 1 and 2. Thus, the measurement data can be used to calculate the homogeneous transformation matrix, which transforms the measurement data from the laser tracker's coordinate system into the robot's base coordinate system. This is achieved by taking the raw measurement data, then rotating it so that the data is expressed with the orientation of the robot's base coordinate system, and then positioning it. Now all measurement data can be expressed in the robot's base coordinate system. Measurement and identification of the tool transformation of the measurement point or points. The measurement point or points, that is the locations in which the SMRs are mounted, should be measured in known configurations in combination with the nominal or actual kinematic robot model, and identified as position transformations from the mechanical interface of the manipulator to the measurement point. The pictures visualize the SMR is offset from the center of the mechanical interface. This offset is called the tool transformation and is highlighted in blue. Please note that it should be offset from the center for improved parameter identification. Due to step 1, we can measure the position of the SMR in the robot's base coordinate system. As there is a kinematic robot model, and the configuration in which the SMR is measured is known, one can calculate the position of the mechanical interface for this configuration. This is highlighted in green. Then the tool transformation can be calculated. It equals the subtraction of the measured position of the SMR in the robot's base coordinate system minus the calculated position of the mechanical interface. This can be done using the nominal or actual kinematic model. The difference ranges around 1 to 5 mm based on the reach of the robot. In the case of the ABB IRB 6700 with a nominal reach of 2.7 meters, this would result in an insignificant error. Identification of the kinematic and compliance parameters from the measurement data. The model, that is in our case the actual DH parameters and the joint stiffness values, can be iteratively approximated by the calibration model which is defined by the equation below. On the left-hand side, we have the positioning accuracy, which is defined as the difference between our nominal robot model and the transformed measurement data. On the right-hand side, we have the identification Jacobian, which is derived from the robot model, and the parameter vector. In the first step, the initial values of the parameter vector are set equal to the nominal DH parameters and the simulated joint stiffness values from the FEM design of the manipulator. Then in the next step one calculates the identification Jacobian matrix for the parameter vector. Please keep in mind that these quantities are defined through the model of the industrial manipulator. Then forward kinematics and the parameter vector are used to calculate the nominal position. Then one can continue by calculating the gravity torques or torques due to external wrenches. Then one calculates the position differences for all configurations. The number of calibration configurations ranges from around 100 in the industry to several hundreds in academia. Then there is an almost equal number of validation configurations, which is used to validate the calibrated robot model. This is visualized in the simulation and the video of the ABB 6700. The robot approaches a configuration, stabilizes, a measurement with the laser tracker is taken, then the robot continues to the next configuration. The graphs visualize the measured and simulated data in terms of the actual and nominal positions. Once again, from this data one calculates the position differences for all configurations. Then the pseudo-inverse of the identification Jacobian together with the position differences are used to approximate the parameter vector delta. This is shown in the equation below. The parameter vector delta is equal to the pseudo-inverse of the identification Jacobian multiplied by the position differences. Then one can add the parameter vector deltas to the initial parameter vector and loop through this approximation until the position differences converge to a stop criterion. The stop criterion is usually close to the repeatability of the manipulator. End. Thank you very much. This concludes the video on 3 essential steps of the kinematic and compliance calibration procedure. The robot models and the algorithms for parameter identification are available in the referenced scientific literature or upon request from the presenter.